we'll be looking at quadratics. So our first section is we're going to look at patterns, and the notes are called a different type of change. So for the warm-up, look at the patterns in the three tables. What do you notice? What do you wonder? So if you look at the first pattern right here, you can see that it's going up by 5 every time. And if you remember from last unit, that would be our common difference. So you could say things like the common difference is 5. You could say the slope is 5. You could say, you could write the recursive equation, you could write the explicit equation, you could say it's arithmetic. You could say it's linear. So there's a lot of things that we know about the first pattern in the first table, which is going up by 5. In the second table, we can see that we're multiplying by 2 every time. So you could say such things like the common ratio is 2. You could say it's geometric. You could say it's exponential. You could write functions, a recursive equation or an exponential function to represent how you get from one term to the next. So it's a good kind of carryover from what we did last unit. If you take a look at the next one, though, if you notice it goes from 8 to 11 to 10 to 5 to -4. It's something we haven't seen before. We're not adding the same number every time. If you try to find a common ratio, there's not a common ratio for this one. Let's take a look at what these look like if you graph it. So in class, we'll be pulling up Desmos and graphing these tables just to see like what they look like. So I'm just going to pull up Desmos. And we can actually put tables into Desmos. So if you do the plus, you can add a table. And let's graph the first one. We knew it was linear. And so it goes up to 5 for the x value. And for the y value, it starts at 0 and goes up by 5. Okay, so if we zoom out, or I can drag this around, we can see that it's linear. You have that constant change, that slope of 5. Let's add another table and put in our second pattern. This one will be red. Goes up to 5, and it started at 3 and doubled every time. And we can see that that equation, exponential, did I type that in right? No, I didn't. Whoopsies. Okay, so that should be 48. We can see the exponential growth there. It starts out looking kind of linear, but then it just grows really quickly. So there's that pattern. And let's add our last one in just to see what does it look like. Okay, so this one starts at 8, 11, 10, 5, -4. All right, so this one, if we zoom in, it starts to go up and then it goes down. So this is definitely not arithmetic or geometric. And we have to figure out what type of change is being represented here and what type of function is this that makes this kind of curve looking down. And so if we zoom in, we can figure out like, okay, what is going on here? So if we look from 8 to 11, the change in that, like if it was arithmetic, you would be adding 3. But then you would subtract 1, subtract 5, subtract 9. So this is how you can tell it's not linear. But watch what happens if you do the difference between it's called the second difference here. So the second difference, how do you get from a 3 to a -1? You can subtract 4. And then a -1 to a -5, subtract 4 again. And a -5 to -9. So in this pattern that makes this, again, we graphed it, looks something like this. That second difference is the same. So in a way, it's similar to arithmetic because you have a common difference, but it's just the second common difference is the same. So today we're going to be looking at a few problems illustrating this new type of change that we're looking at. So the first one's measuring a garden. So in this problem, Brennan has 50 meters of fencing to completely enclose, let's highlight, a rectangular garden in the backyard. Can you draw some possible diagrams of Brennan's garden? Can you label the length and the width of each garden? Okay. So our first garden, it could be really thin. It could be one, it's like this blue. Okay, so long and skinny could be like 1 by 24. And if you add 24 plus 24, that's 48, plus the 2 on the end, that's 50. So here we've used the 50 meters of fencing, and our garden can be long and skinny. Okay, we can make it a little bit shorter and a little bit fatter. So this would be 2 by, and that would have to be 23. So again, if we add 23 and 23, 46, 47, 48, 49, 50, that adds to 50. And we can keep going. You can kind of notice a pattern here. What if we make this 3? How long does it have to be? And it would have to be 22 meters long. So again, if we add up all like the perimeter of this, we would get 50 as well. And let's do one more. So again, and I haven't drawn it to scale, obviously, but 4 and 21. These would all work. Not the only ones that work, but I don't know, I like going in order, so I would find these and they would all work. So then it says find the length and the width of such a rectangle that would produce the largest area. So we'll review in class the area of a triangle, base times height, or length times width. And then it says explain or show why you think that the pair of length and width gives the largest possible area. So let's just start calculating the area. The first one is 1 times 24, 24. The second one, area equals 23 times 2 is 46. 22 times 3, 66. 4 times 21, 84. So we can see our area is getting bigger as this rectangle gets a little bit fatter. So number 2, it says find the length of such a rectangle that would produce the largest possible area. So in class, we'll explore different ways to go about this. I would probably make a table. So in my table, I would look at the side lengths. And we could look at the areas. So if you continue with the pattern here, we would know that if one length was 5, then the other would be 20. So again, look at this pattern that's happened in our first 4 examples, and just kind of piggybacking off of that, here's what I came up with. And then we can calculate the areas. And we can see, and then from 12, 13, it just reverses. So we could keep going, but, and what I mean by that is it would be 13, 12, 14, 11, and then you can see it's kind of a mirror image of the side here. So here's our largest area, which is 12 by 13 or 13 by 12, and it says explain or show why you think that the pair of length and width gives the largest possible area. Well, I made a table and we showed it that way, but there's definitely other explanations for that. All right, let's graph it. It says plot some values for the length and the area of the garden on the coordinate plane. All right, so let's do the first one, which is if our area is 1, if our side length is 1 and 24, the area is 24. So let's graph that. 1, I'll graph it in purple. So 124 is like right here. But also 24, 24. It's like, ooh, that's 25. It's like right here. And then we have, I'll skip a few and do 4, and I'll do 5. 5 and 20 are both at 100. Okay, so 5 is at 100. 20 is at 100. All right, I'll skip a few more. Let's do 10 and 15 are at 150. 10 is at 150. 15 is at 150. And let's graph the maximum. 12 and 13 are at 156. 12 and 13 are at 156. So here's like the maximum there. So you can see what shape this takes, and you can also see that it's symmetric because it goes up and then it goes down. So this is the new pattern that we're looking at, and we're going to be studying this in depth this unit. So for number 4, what do you notice about the plotted points? We notice the shape it makes. We notice that it's symmetric, right, because it just flips like we talked about. So we'll ask each other in class, what did you notice? Then it says number 5, the points 366 and 2266 each represent the length and area of the garden. Plot these 2 points. All right, and we had that right here in our green example, so let's plot those. 366. And what was the other one? 22. Okay. So approximately there. It says, what do you notice? What do these points mean in this situation? So what it means is if the length or width is either 22 or 3, the area is 66. Could the point 125 represent the length and area of the garden? Explain how you know. And, okay, one way is we could draw it out, right? So 1 and 25. And we know this is not possible because this area is greater than 50. So we know it doesn't work. So summary, we looked at this different kind of change right here. We graphed it. We saw this new shape that it made. And we learned that sometimes 2 different inputs have the same output. So like example 5, 2 different inputs have the same output, and that happens for a lot of these points, and we can see it makes a mirror image of itself. So in class, you'll be working through just page 4 in your packet, again looking at patterns and trying to look for characteristics of this new type of function that we're learning. There is a typo though right here, the 10 and 50 doesn't fit, so we'll cross that off in class, and maybe we'll add one more, 347. Which add to 50, and then we'll figure out the product. All right, so that's it. Class will go over any questions that you have.